Hello, everyone. Well, those of you who are watching this video. Uh, okay, so by request of a few of you, today at the end of class, I decided to make this video. I don't know yet if it's going to be short, but I will cover a few examples on optimization, some word problems, and I will also do a couple of area between curves problems. Okay. And hopefully that's all that you guys need really to I guess see me work out, because I said on the exam I will give you an area between curves problem and also an optimization problem, right? So those are going to cover with the examples that I will work on right now. But then the other two problems on the exam will be a derivative that involves exponentials and logarithms. I know that the derivative that I gave you on the second exam was a bit hard and lengthy. This one won't be like that, at least not as bad. And then the other problem that I'm giving you guys will be an integral that requires u substitution with change of bounds. But that I think is not too bad, right? So yeah, I'll just go ahead and start working these problems out. So I'll now start sharing my screen. OneNote. Okay, so this is the first optimization problem. It's about enclosing the largest area. Let me see. Put this over here. Let's make sure that this is working properly. It is. Okay, enclosing the largest area. The owner of the Rancho Los Feliz has 3,000 yards of fencing with which to enclose a rectangular piece of grazing land along the straight portion of a river. Okay, so there is this river, right? So let's say is this, and then there is this straight line portion next to which we are going to use this 3,000 yards of fencing to enclose a rectangular area. So I guess it's not hard to see that it will be something like this, right? So something like this. Okay. If fencing is not required along the river, of course, right? Like on this area, on this side of the rectangle doesn't need fencing. What are the dimensions of the largest area that he can enclose? Okay, assuming that the owner is a guy. Okay, so this is the river, right? That doesn't need that on that area, that side of the rectangle doesn't need a fence. Okay, let's see. All right, so remember that whenever we are working, we are doing a problem of this kind. We want to go through some steps. Well, the steps that I gave you before are suggested steps, right? They keep the whole process organized. And I want to do that, right? We want to keep things organized so that we can then go back and make sure that we didn't make mistakes anywhere and so on. Okay, so the first step is to draw the scenario that is being described to you, right? Which we just did. Rectangle next to a river. We know that the side of the rectangle that is on the river or on the edge of it doesn't require a fencing, but the rest of it will. So we have these two sides and then this long one, right? Okay, now the second step is to then write down variables and measurements that matter, right? So measurements or quantities that matter. Okay, well, we are looking at a rectangle and we are looking at the largest area that we can enclose. Well, clearly, the measurements that matter here will come from the sides of the rectangle, right? We know that these two sides are equal, right? And then we have this other one, right? So we can choose two letters for them, right? We can choose X for here and then Y for here. But because the problem is asking us about the largest area that we can enclose, then area, the overall area of the rectangle, is also another quantity that we want to keep in mind, right? So X and Y as dimensions of the rectangle, and then area itself, right? So those are the measures that matter, and those are the letters or variables that we are choosing for them. Okay, now the next step is to write down an expression for the quantity that we want to optimize. Okay, so expression for quantity to optimize. Okay, so we know that that is area, right? Because the problem asks, what are the dimensions of the largest area that he can enclose? What is this area, right? We know that that is area, for which we chose the letter A, right? So what is that expression? Well, the area, the expression will come from the area formula for the rectangle, which is based on height, right? Area is equal to, then base, we chose base to be, well, let's see, one of these, right? Let's say X, and the other dimension is Y, right? Okay, now this is our expression. We know that the next step is to make sure that expression, this expression to optimize, depends only on a single variable. At this point, it depends on both X and Y. It's a function of two variables, X and Y, right? So we need to change that, right? This is right now a two variable function, and we don't like that. We want to change it into we need to make it into a single variable function, right? Well, for that, we will need to use the information given in the problem. The problem says that we only have 3,000 yards of fencing, and we need to use it all, right? Okay, so what does that mean? It means that the sum, like the perimeter, right, will always need to end up adding up to 3,000, right? So we can do that. We can do that. I mean, with what I said about the perimeter, we can already say the following. We can say that X plus Y is equal to 3,000, right? This is the perimeter. We know that we don't have to include this side over here, so that's why I'm not adding Y twice. I'm adding it once only, and then 2x, right? So 2x plus Y is equal to 3,000. Okay, now you see that you can solve for Y, and that will give you 3,000 minus 2x. And this is what we want, right? Because then this allows us to come back here to this formula and replace this Y with the expression here. So that then the expression for area depends only on X, right? So that's one way of doing it. Now, at this point, also, well, before, instead of using the idea of perimeter here to write this equation, we could have just, so that this is X, this is also going to be X, and, the total fencing is 3,000. So then, of course, this is going to be whatever is left from 3,000 after using X twice, right? After using 2X of fencing. So then the remaining fencing that goes onto this side will be 3,000 minus 2X, right? Which is exactly the same thing that we got over here. But this other way of doing it is more intuitive, right? You didn't need to write the equation and solve for Y. You can just look at the rectangle, see which sides you are already taking into account, X and X, and then just take that away from 3,000. Okay, but the moral here is that we can replace Y with 3,000 minus 2X, right? So if we do that, we can then write X and then 3,000 minus X. Oh, no, sorry, 2X. Yes, 2X. Okay, now A depends only on X, right? The expression depends only on X. So we can write now A as a function of X. Remember that the notation that we use for that is parentheses X, right? So A of X. This means area A as a function of x. Okay, and you see that you get x times 3000 minus 2x. This, you guys should be able to recognize this already as a parabola, right? Because when you distribute the x, you are going to end up with some x squared in there, and then x, right? Without constant term. But that's the standard form for a parabola, right? And in fact, you should also see that the way it's written now, you see that it's written as a product of two linear terms, right? X and then 3000 minus 2x. This is a very nice way of having it written down because it tells you also what are the roots, right? If you set it equal to 0, then you know, this gives you x equals 0, and then this gives you x equals, what is it? It's then 3, so 3000 is equal to, let's do it step by step here. 3000 minus 2x equals 0. You send this 2000 to this 2x to the other side. So 3000 is equal to 2x. Divide by 2, you get x is equal to 1500. Right? So your two roots are x and this. And so those are your roots, right? Okay. Now you want to see what is the sign of the coefficient multiplying x squared, because that tells you if it's, you know, opening up or opening down. Well, you see that that will come from x times minus 2x. That will give you minus 2x squared, but it's a negative number. So it is going down like this, right? And it makes sense because, you know, we're looking after a largest area. And if this function over here tells you the area, of course, if there is a maximum, you expect the parabola to be opening down, right? So that the tip is the maximum, right? Okay, but we know that the function looks like this, and we also know the roots. It crosses the x-axis at 0 and at 1500. So if this is the x-axis, then this is 0, and this is 1500, right? And of course, then this will be max here. By symmetry, you could already solve the problem, like right away. You know, you just find what is the point in between, because this parabola must be symmetric, and the point in between is where the maximum happens, and so on and so on, right? But that's not how we want to solve this problem. You could do that, but we want to use the optimization process learned in the previous section, right? Okay, so, all right, I think this is all information that is useful, but let's do like we don't know that, okay? Okay, let's instead multiply this out to get our parabola. So remember that x times 3000, that is just going to be 3000x, and then minus 2x, that gives you, or times x, that's minus 2x squared. We want to rearrange it so that it looks like a polynomial that's going down, descending order of power. So minus 2x squared, and then plus 3000x. Okay, so this is the expression to optimize, right? This is our expression to optimize. Let's see. I want to move this over here, and I want to write, this is the expression to optimize. Okay, let's use this color, green. Okay, now let's recall that for optimization, it's not only a function that we need, we also need an interval of optimization, right? So for optimization, the optimization process, we need an interval. Okay, so from the graph that we drew before, remember that I drew this graph, right? We know that the function looks like this, right? This is 0 and this is 1500. We know that the interval of optimization, of course, is going to be this one over here, right? Because area has to be positive, right? This side of the function and this side of the function have negative y values, but that means negative areas. So those areas don't make sense. Of course, we don't want to consider them. We only want to consider this part over here, because area here is positive, right? So then we could say that our interval is going to be from 0 to 1500, right? By inspection, we can make that conclusion by looking at the graph, okay? But, you know, that's not the case all the time. You sometimes have a function and you don't know what the graph looks like. Okay, well, in the case of an exam, for this type of problem, you will not know that, right? The graph, I mean, you should be able to figure that stuff out though by yourself. But there are other ways and easier ways to figure that out. And it comes from making the following conclusions. So how do we find this interval of optimization? Well, we know that the dimensions must be positive, right? Well, I guess they do not make any sense as being negative, right? So they're either 0 or positive, right? So then we know that x is at least 0, greater than or equal to 0, and the same goes for y, right? Okay, so this tells us already that our interval of optimization starts at 0, right? But now, what about the other one? What about y is greater than or equal to 0? Well, this y over here, we replace it with what we got here. We know that y is equal to 3000 minus 2x, right? So we just replace it. We just replace, sorry, I don't like that curve. Right, we just did that. We just replaced the y with 3000 minus 2x, and that is still greater than or equal to 0. Right, now if you solve this inequality, you can send this minus 2x to the other side, so it's gonna go with positive sign, right? So 3000 greater than or equal to 2x, and now we divide by 2 both sides, right? Divide by 2, divide by 2, you get then 1500 greater than or equal to x. So x can be at most, right, 1500. X is less than or equal to 1500. So then this gives you the other end point of your interval of optimization. That's gonna go here, right? Okay, you see that it's exactly the same as what we got here by looking at the graph. Right? Okay, so then we are ready to optimize. We have our interval of optimization and our expression to optimize, right? So remember that the steps to do optimization are finding critical numbers in the open interval, computing the y values of those critical numbers and of the endpoints, and then we need to rank, right? We look at all those y values and recognize the max and the min. So let's go ahead then and do that. Okay. Expression to optimize and interval of optimization. So first, so now we are doing optimization, right? So optimization process with area function minus 2x squared plus 3000x over the interval from 0 to 1500. Okay, so critical numbers. Remember that critical numbers are the x values such that the derivative becomes undefined or the derivative becomes 0, right? Well, the function itself, the original function, the area function is a polynomial. So its derivative will be, again, a polynomial, right? So, I mean, let's go ahead and find the derivative. So it's going to be the derivative of minus 2x squared plus 3000x, derivative of this. Derivative of this, well, again, well, the second power comes to multiply in the front, multiply with -2, that's going to be -4, right? And then the second power goes down by 1. So that's just 1 power 1 x. And then for this part, the x disappears, right? And we are left with 3,000, right? So that's our derivative. You see that it's a straight line, right? This is a polynomial of degree 1, straight line. So you see that, of course, then there are no x values that make it undefined, right? Polynomials or straight lines have domain everything. They are continuous everywhere. They don't have a point where they become undefined, right? So then we don't need to worry about this type of critical number. We only need to worry about this type of critical number, right? So then for the x values that make the derivative equal to 0, we just need to set the derivative minus 4x plus 3,000. We need to set it equal to 0. We now solve for x. You can send this negative 4x to the other side. It's going to go with positive sign. And then we need to divide by 4. Right? So then this gives us what? This gives us that x is equal to 3,000 divided by 4. 3,000 divided by 2 is 1,500. And then 1,500 divided by 2, that's 750, right? Right? Okay, so then this is our only critical number. You see, so in other cases, we have had problems where we get many critical numbers, right? But we discard some of them based on the interval of optimization that we are working with. In this case, this critical number falls inside. Exactly, it's like right in between 0 and 1,500, right? So we can keep this one, right? Okay, so then, so this is our only critical number. The next step is to compute the y values. And remember that you need to compute the y values of the critical number that we found, and also of the endpoints, which are 0 and 1,500. Right? Now, when it comes to this part over here, to plugging in these x values to get the y values, it would be easier to play with the function for the area, but the one that we wrote first, like this one up here, instead of using this one over here, right? Why? Because, well, we are going to plug in numbers this big, and squaring that is not going to be fun, right? Or multiplying it by 3,000 again, that's not going to be fun, right? So it's going to be easier to do it with this one over here, and you will see why. I mean, that's usually the case. Okay, when plugging in to find the y values, just go back to the very first expression that had, you know, the linear terms multiplying each other, right? So let's see. We want to use this version of the function. Okay, so a of 0 is what? Well, if you plug in 0 here, I don't care what I get over here, it's going to get multiplied by 0, right? So it's 0. Now, what about a of the other endpoint, 1,500? Well, if you plug in here x, you get there 1,500, and then you have 3,000 minus 2 times 1,500. Now this gives you 3,000, right? 3,000 minus 3,000, that's 0. 0 times 1,500, 0, right? So this is 0. Awesome, right? So you see that in these two numbers actually make sense, right? Because when we were looking at the graph here, you see that those two are roots. So of course the y values there at 0, right? Now we need to compute area of 750. Well, that's then 750 times 3,000 minus 2 times 750. 2 times 750, that's 1,500, right? and then we need to do 3,000 minus that, but that's also 1,500. And then we need to multiply by 750. What is that? Well, you can disregard the zeros. There are 3 of them, and just multiply 75 times 15, and just get that number. And then whatever the number you get there, you tag on the 3 zeros that you kind of like ignored at the beginning, right? So let's see, 75 times 15. Let's see, you can do 15, you can see it as 10 plus 5. So that then gives you 750, and then plus 75 times 5, that is 5 to 35, 37. So 375. Right now you need to add 750 to that. You get 5, 12, and then 11. 1125. So 1125. That's what we got by multiplying 75 and 15. But there are still the other 3 zeros, right? So then we need to include them now. 1, 2, 3. So you get 125,000 as our area, right? So that is going to be the area that goes in there. Like that is the maximum value up here. Okay. And of course, the next thing is to rank them. The next thing is to rank Y values, right? But of course, the Y values that we got are either 0, 0, and then this big number that we got. So of course, that's going to be the max, right? So we know the max. So then our answer is going to be the units were yards, right? But because this is an area, then this is going to be yards square, right? So it's the largest area. But remember that the problem also asks us about the dimensions, right? So the dimensions will come from X and Y, the values for X and Y. For X, we know that that is 750, right? Because that's the X value where the largest area happened. Now for Y, we can use the formula or the equation that we got over here, which then gives you 3,000 minus 2 times 750. Remember that this is 1,500, right? And so 3,000 minus 1,500, that's just again 1,500. So these are the dimensions. And of course, they add up to 3,000, right? Remember that we used X twice for here and here, and that's 1,500. And then 1,500 for this part over here, right? 1,500 plus 1,500, 3,000. Okay, so those are then our answers for the problem. I hope that this explanation made sense. I tried to organize the whole process by just following the steps that I suggested before, right? Measure, we first drew, we then wrote down the measurements or quantities that matter, dimensions of this rectangle and then the area. Then we identified the expression that we need to optimize. That's the area, X times Y, but then we replace the Y with this equation that we got from looking at the perimeter and the available fencing. And so that way we ended up with an expression for area that depended only on a single variable, on X. And then we got our interval of optimization, right? By just realizing that both dimensions need to be at least 0. And then after that, we just follow the typical optimization process, for which we found the critical numbers. And then we computed the Y values of critical numbers and the endpoints of the interval of optimization. And then we just ranked them, right? But then the ranking was easy because it was all zeros and then one super big number. and then we answer to the questions that they asked us in the problem. One of them was dimensions, and then the other one was what is the area? There they are, right? Okay, so I hope this made sense. Let's now move on and try this other problem. This was a metal fabrication. So this is, it says, if an open box is made from a tin sheet that is 8 inches, that is an 8-inch square, right? So it's a square where all the sides are of length 8 inches. Okay, so we are making an open box from this material by cutting out identical squares from each corner and bending up the resulting flaps. Determine the dimensions of the largest box that can be made. Okay, so we did an example like this in class, I think, where we didn't start with a square, we started with a rectangle. But we also were given the dimensions of the initial rectangle, right? So, so let's draw, right? The first thing is to draw the scenario. So to draw this scenario, we just need to draw a square. Hopefully this is as close as I can get to square. I think so. Equal sides. So pretend all these sides are straight and equal in length. And so we are making cuts on the corners, right? We are cutting out identical squares. So this square over here, this square over here, here, and here, right? So that we then bend up the flaps and make an open box. Right, so this is going to turn into something that looks like this. See, dot, 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 and then dot, dot, dot. Right, the base of that box is it's a square, right? Because if we delete x here, x here, x here, and so on and so on, this part over here is a square too, right? The remaining base is a square. Okay, all right, so that is our drawing. Now we are cutting out identical squares, right? So let's see, this square over here has sides all of the same length, right? Let's call that x, right? So this is x, this is x, this is x, this is x, right? And it's going to be the same for every other rectangle, right? Okay, so of course, then the size of those small squares is going to matter in this problem, right? So then, of course, then that's going to be one of the variables or one of the measurements or quantities that we need to write down. So quantities that matter. Because they don't tell us how big these little squares they are, right? So that's why we can go ahead and just call it x. So x is a quantity that matters. Now the other quantities that matter, let's see. So the question is about determining the dimensions of the largest box that can be made. By the largest box, they mean, you know, if a box is large, if it can contain a lot of stuff, right? So its volume is big, right? So of course, then volume, it's going to be of importance here. By finding the largest box, they mean optimized volume, like give me the maximum volume that this box can have. So then, of course, V is another letter that we want to choose for that, right? So these are two, so size of squares that are cut out, and then the volume, right? Okay, so those are the quantities that matter. Now, the next step is to write down the expression to optimize, right? Okay, so then that's going to be, of course, then the volume. We know that the volume is what we want to optimize, right? But then we need to write an expression for the volume. Okay, so then for this, we will need to go back to our drawing here. Okay, so if we remove X here and remove X here also, right? Remember that this square has dimensions 8 by 8. Right? Okay, so then if you remove X here, and the entire side is has length 8, then what's left here has dimensions 8 minus 2x, right? Because X here sum up to 2x, and then what's left is 8 minus 2x, right? Now over here, the same thing happens, right? You are removing X here, you are removing X here, and so then this is 8 minus 2x, right? So then when we come back to our already built open box, then, you know, this side over here comes from putting these two together, right? And then they give you also then the height of the box, which is going to be X. And these two are the dimensions of the base of the square base. So then this is 8 minus 2x, and this is 8 minus 2x, right? So then the volume will be given by multiplying all those three dimensions, right? The dimensions of the base times the height of the box. So then that is X times 8 minus 2x, 8 minus 2x. So of course, then these are three linear terms. When you multiply them all out, you will get a cubic polynomial, a polynomial of degree 3, right? So it will be something like this, right? A curve that goes like that. Remember that it can for a cubic, it can go like this, or it can go like this. It depends on whether the leading coefficient, so the coefficient of the x cubed term, if it's positive, then it looks like this. And if it's negative, then it looks like this. Okay. Now, also, let's recall that, and this I said before, that the way it's written, the way the cubic polynomial is written right now as a product of linear terms allows us to see the roots of our polynomial, right? So you see that this gives you root 0, and then this gives you root, let's see, 4, right? You set equal to 0 divided by 2, you get 4. And this also gives you root 4. That means that your polynomial will look like this. And this is 4. And this is 0. And you see that if you multiply x minus 2x and minus 2x, you get positive 4x cubed. So the leading coefficient is positive, so it looks like this. Okay, so those are conclusions that you guys, I don't know, I feel like maybe this is too much to expect, but you at least should be able to recognize that you get a cubic polynomial out of this, right? And cubic polynomials look like this, and you could see the roots too. But I don't expect you guys to be able to do all of that for the exam. Okay, so I just expect you to go ahead and multiply this out, recognize that you get a cubic polynomial, and then just go ahead and complete the process, right? So if we multiply this out, what do we get? Let's multiply these two. You get 8 times 8, that's 64, and then 8 times minus 2x is minus 16x, and then minus 2x times 8, again minus 16x, and then minus 2x times minus 2x, that's positive 4x squared. You can combine these two, you get, oh, sorry. Let's rearrange this for x squared, let's put it in the front. Minus 16x, that's minus 32x. And then we have the plus 64. Okay, then we can multiply the x in. We get 4x cubed minus 32x squared, and then plus 64x. Now, remember that we are going to do next the derivative, right? And then set it equal to 0. So all of that process is going to be, it'll be made easier if we go ahead now and factor out a common factor. So you see that the constants, the coefficients are 4, 32, and 64. They all are multiples of 4. So you can factor out 4, and then you're left with x cubed minus 8x squared, and then plus 16x. Okay, when we take the derivative of this, the 4 in the front can be disregarded, and we just worry about the cubic polynomial, right? Okay, so this is our expression to optimize. We managed, well, it wasn't too complicated to put it in terms of a single variable, right? It's a function of x, that's why I'm writing v of x. This is not v times x, it's v of x. Okay, what other thing do we need before optimization? We need our interval of optimization, right? Okay, so let's see. So we can do the same analysis that we did before. We know that the dimensions don't make sense as being negative, so they have to be at least 0, right? So x has to be at least 0. And also, the other dimension involved is 8 minus 2x, right? 8 minus 2x also needs to be at least 0. So this gives us one end of the interval, right? It's going to start at 0. Now this one will give you the other one. So when you solve this inequality, you send this to the other side as positive. So 8 is greater than or equal to 2x, and then divide by 2. And you get 4 greater than or equal to x. So that means that x can be at most 4. So then 4 goes here. Okay. All right. So this is going to be then our interval of optimization. Okay. The rest of this should be pretty much the same as before, right? You find critical numbers. For the critical numbers, of course, well, let's do some of that work. Okay. I don't want to spend too much time and make this video super lengthy. I feel like after this, you know, with the function that you want to optimize and the interval of optimization, you can already complete the process by yourself. Okay, so, but let me get you started at least. So optimization process. We have our function, right? The function that we are optimizing, and our interval of optimization. So we are ready to start that. For the critical numbers, you need to, so for critical numbers, of course, there's no going to be, so we need to take the derivative. As I said, we can disregard the 4, and we can just take the derivative of the polynomial. That is 3x squared minus 16x, and then plus 16. Sorry. Right? And we need to set it equal to 0 or find the x values that make it undefined. But this is a polynomial, so no x values make it undefined. We just need to set it equal to 0, right? So when you set it equal to 0, you can divide by 4, and you end up then with 3x squared minus 16x plus 16 equal to 0. 0 divided by 4 is just 0. And then this, you can just put into linear terms, right? This 3x squared turns into 3x and x. 16 becomes, let's see, oh, just 4 and 4, right? And both have to be negative, because then you get this gives you 12 minus 12x and then minus 4x, and they both add up to negative 16x, right? So you get 3x minus 4 and x minus 4. You set h equal to 0, and from here you should get 4 divided by 3 and x is equal to 4. Are they both in the interval of optimization? Well, 4 is exactly the endpoint, right? So yes, it is, because the interval of optimization includes 4. So 4 is in there. 4 divided by 3, that's a number, what is it? If it's slightly bigger than 1, right? 1.33333, right? So that's going to be in the interval of optimization. So this time we get 2 critical numbers, and we keep them both, right? So then for the y values, we need to compute the y values of 4/3, of 4, and then of the endpoints, 0 and 4. 4 is already there, so we just need to include also 0. Right? But yeah, this is then stuff that you can do, right? You just plug this into your function, your volume function, compute the volumes, and then rank them and get your maximum. And it should actually be this one over here. Okay. So I'll leave that up to you guys. I don't want to make this video super lengthy, so I'll just move on to the next problem, the next two problems, which is area between curves. I'm going to do something similar. I will just work one of them out entirely, and then leave the other one just, just do the main steps. I think I want to do this one fully. Okay, and the other one, I'll just set it up and you guys will continue. Okay, so this one over here. So this was from a section of exercises from 35 to 42. And it said the following: sketch the graph and find the area of the region completely enclosed by the graphs of the given functions f and g. Well, f is minus x squared plus 4x, and g of x is 2x minus 3. Okay, so we need to use the sketch, right? So I use Desmos to get this image over here. And when it comes to these problems, I will always give you the image. Okay, I'll always give you the sketch of the two functions. And of course, I just want to focus on the area that is entirely enclosed between them, the region between the two curves, right? So I did that with Desmos. You can do, of course, you can do that also with your homework, okay? So we are going after the area here, the area that is entirely enclosed by f and g. Now, I haven't labeled here which of these curves is f, which of these curves is g, but you guys should be able to figure that out on your own already. Because f, you see, it's a quadratic, it's a polynomial of degree 2, so it's a parabola, right? And of course, of these two lines here, the parabola is the red one, right? This is f of x. And g of x, it's 2x minus 3, that's a straight line, right? Polynomial of degree 1. So then the blue line is g of x. Okay, and this is a fundamental step, right? Because remember that when you're finding area between curves, you want to know which function is on top, which function is below, right? By looking at this region, you can already see that f of x is the one on top, right? And the one below is g of x. Okay. All right, so how do we approach these problems? Well, we already recognize that f is on top and g is below, right? The first thing that we need to do is we need to find the intersections. Right, because so far we know that our integral will go from somewhere to some other point. And we know that over here, it will be f of x minus g of x, because we saw by the image that f is on top of g, right? So it's always the one on top goes first and then minus the other one, then dx, right? But in order to know the bounds, we need to find the intersections of f with g. So for the intersections, we just need to set the functions equal to each other. F of x is minus x squared plus 4x, and g of x is 2x minus 3, right? We need to solve for x here. Well, you should do just put everything on one side. So 4x, and then this 2x comes with negative sign, and then this minus 3 comes with positive sign, and we are left with nothing on the right side. We can combine like terms now. 4x positive minus 2x, that is positive 2x, and then you have plus 3 equal to 0. These are nice numbers. We can see, put this into a multiplication of linear terms. Okay, so minus x squared, then that will come, of course, from two x's, one with negative sign. And then 3 breaks into the only possibility is 3 and 1, right? But we just need to pick them in the right order. So what do we want? We want 3 to stay positive and 1 to stay positive. And do we want them like this? Minus 3x plus x? No, that's not what we want, right? We want 3 times 1 like this, because then we get 3x minus x, and that is 2x, right? So then those are minus x plus 3, and then x plus 1 are our linear terms. We said each equal to 0, and what do we get? This gives us x equals 3, right? Minus x goes to the other side with positive side, so then x equals 3. And then x plus 1 gives you that x is equal to -1. Okay, so then these are your two solutions, and they show up on the graph, right? So you see this point over here on the x-axis is -1, and the other one over here is 3. Sorry, I just covered the 3. This is 3, right? So this point over here is x, has x component 3, right? So then your integral will be from -1 to 3. And then it's f of x minus g of x. F of x is minus x squared plus 4x, and then minus g of x, which is 2x minus 3. And then, of course, don't forget to write dx. What do we get here? Minus x squared plus 4x. Let's get rid of parentheses, minus 2x, and then plus 3. These two give you 2x, right? So then your integrand is minus x squared plus 2x plus 3 dx. Okay, this is we're integrating a polynomial. That should be super straightforward, right? So let's do that. Minus x squared turns into minus x cubed divided by 3. And then the 2x, well, the 2 you can disregard it. It's just a constant multiplying, and the x becomes x squared divided by 2. And for the plus 3, that's just 3x, right? You tag on an x. And your bounds are from -1 to 3. Remember that when you do integration, you no longer write the integration symbol here, the long s. You don't write it. You now just use brackets and keep your bounds. You can simplify these 2 and these 2. So this becomes minus x cubed divided by 3 plus x squared, and then plus 3x from -1 to 3. The rest is now plugging in those numbers and taking the difference, right? So we need to first plug in 3, minus 3 cubed divided by 3. Now notice here that the minus sign is not being cubed. Only the x term is being cubed, okay? Then plus 3 squared, and then plus 3 times 3. Okay, so that's what you get when you plug in 3. Now we need to do minus, and then do the same with -1. Minus, and then -1 cubed divided by 3 plus -1 squared plus 3 times -1. Okay, so let's see. This 3 cubed, the power 3 can go down by 1 because there's a 3 in the denominator, right? So then that becomes 3 squared, that's 9. But there is a negative sign in front, right? So you get -9. Now you have this plus 9 and then this other 9. So 2 of them cancel each other out, and you're left with a single 9. Okay, now over here, you see that -1 cubed will give you a negative number, right? Because negative times negative times negative gives you a negative. So then it will be negative, and 1 cubed is just 1, right? So you get -1. Okay, so this part over here, it's a -1, but there is a negative here too. So then that will give you something positive, right? So 1, and then you have 3 in the denominator. Now, -1 squared, that makes it positive, so +1, and then 3 times -1, that's -3. 1 and -3 give you -2. But then 2, you want to see 2 as 6/3, right? So you can combine fractions. So 1 minus 6 minus 5 divided by 3. Okay, so these brackets gave you -5 divided by 3, and the other part gave you 9. Okay, so then your brackets are now gone, and you can just write 9 minus 5/3. Oh, wait. I'm making a mistake there. The bracket here gave you -5/3, but there is a minus there in between, right? That minus is going to be applied on 5/3, and it makes it positive. So you actually have 9 plus 5/3. You can see 9 as 27 divided by 3. Right, you want to make it into a fraction with denominator 3, and 3 times 3, and then plus 5/3. 27 plus 5, that is 32 divided by 3. 32 cannot be divided by 3, so this is then your answer for that part. Okay. So this should be it for this problem. Yes, yeah. Okay, so I hope this made sense. I don't think it was complicated. This looks like a kind of problem that I could test you on. You know, sometimes when you do these integrals, things get out of control when you have a polynomial. Because remember that when you do integration of a polynomial, the polynomial goes up like in its degree, right? So you see that we integrated a polynomial of degree 2, and the result is a polynomial of degree 3, right? So when we plug in stuff, we need to cube numbers, right? So the thing is that when your polynomial ends up being of super high degree and you need to plug in numbers, then things can get messy and nasty, right? Especially if you are plugging in the numbers like 10 or 30 or 20, you are cubing or raising to the 5th power, and so on and so on. That can get nasty super fast. But I feel like if you choose then your functions to be just like, simple things like a polynomial of degree 2 or a polynomial of degree 1, then, it's not too bad. It's not too bad, right? Because I don't want to give you integrals where you get lost in this part over here when you plug in numbers. I don't like that, because that's not the point of calculus, right? You do calculus up to the setup. After that is all algebra or arithmetic even, right? And that's not what you're learning in this class. You're learning how to set up these things over here and what they mean, like knowing what they mean and so on and so on. Okay, so this is the answer, 32 divided by 3. Let's set up the other one. Okay, I don't want to spend too much time on this one. Okay, so in this problem, we were not given the functions explicitly like in the previous one. They are still given on the image though, but they gave you instead an image. And they shaded some regions, and then they said, find the area of this shaded region. Okay, so the difference that there is with the, between this one and the other one is that in this one, you are given an interval of integration. Okay. In the previous one, you were not given one, you needed to find it yourself. But when you're given one, it's easier, right? Because, I don't know, you could be doing something like this and something like that. And if they said, do this and this, then of course, these are just, this is A, this is B. You can just set up your integral very easily, right? From A to B of f minus g dx, right? But this specific example that I've chosen has a bit more than just that, right? So this this bound over here, it's an easy bound, right? You integrate up to -1. But over here, the bound coincides with an intersection, right? And also, here's the other thing. On this region over here, the function on top is, this is x squared, right? So this is x squared. And the function below is x to the 1/3, which is the same as cubic root of x, right? So cubic root of x is here. So you see that for this region, x squared is on top and the other one is below. But for this region over here, the rules change, they switch. Now the cubic root function is on top and the x squared function is below. That means that when doing the integrals, we need to write two integrals, right? Because remember that a single integral has one function on top throughout the entire interval of integration, right? So, and so if there's a change in which function is on top, then we need to do one for when this one is on top and another one when it's the other one is on top, right? So we will need to do here two integrals. Okay, so by looking at the shaded region, we see that we'll need to consider two separate subregions. Since the function on top is not the same for both subregions. Okay, alrighty. So let's see, how do we set this up? Well, so this region over here goes from -1 to here. Okay, that by looking at the image, we see that then that goes up to 0, right? This is the x value here is 0. But we should actually do it by computing the intersections. Okay, in fact, that's going to be helpful also for then knowing where is this other point here, right? Well, it's given to you here, okay, but I want to show you still how to get those intersections algebraically, just by doing algebra. And you know, that way also show you that you get exactly the same ones that you can presuppose by looking at the image, right? Because just by looking at the image, you can see that, okay, the first region will be, well, the one on top function is x squared and the other one below is the cubic root function, right? So x squared minus that, and it goes from -1 to 0, right? So that's the first integral. And then you need to add the integral that goes from 0 to +1. And the one on top then is cubic root of x, and then minus below is x squared, right? Quick setup. And this is correct. It's totally correct, right? But just to show you guys that you can do also this by finding the intersections yourself, you just need to set x squared equal to the cubic root function. Okay, mainly I mainly want to show you how to solve this equation. Okay, because this could show up in the future again, like on the final exam. So how do we want to do this? You could do the following. You could divide both sides by x raised to 1/3, but I don't like to divide by x. Usually that's not a safe move. Okay, what you want to do is you want to put everything on the same side. And in that case, this is what you get, right? You move this to the other side and it goes with negative sign. And once you have it like this, you want to factor out x raised to 1/3 for both. Okay, so of course, this is going to then give you 1. And what is it going to be left here? Well, it's going to be some power of x, right? But we don't know the power. Well, remember that when you plug it back in, you should get back your original expression, right? So if you multiply these two in, the two powers add up to 2, right? So that means that this power over here comes from 2 minus 1/3. And 2 is 6/3. And so then you get 5/3, right? So then your power up here should be 5/3. thirds. And you can, just test it by plugging back in x raised to 1/3. If you multiply these two, the powers get added up, right? And so 1/3 plus 5/3, that's 6/3. 6/3 is 2. So you get back x squared. And then x 1/3 times -1, you get back negative x raised to 1/3, right? So this factoring is then has been done correctly. Okay, equal to 0. Now we just need to set each equal to 0. So x 1/3 is equal to 0. You get rid of the 1/3 by cubing both sides. Then you're just left with x, and then 0 cubed is just 0, right? So x is equal to 0. Now the other one, you set it equal to 0, move -1 to the other side, right? And remember that x raised to the 5/3 is the same as, the denominator is the index of the root, so cubic root, and then the 5 in the numerator is the power, right? So what you have over here is this. You want to get rid of the cubic root by cubing both sides. So x to the 5th, 1/3. Well, 1 cubed is just 1, right? And then x to the 5th is equal to 1. To get rid of the power 5, you need to take the 5th root, right? So but then this cancels each other out, and then the 5th root of 1 is just 1, right? And so you get this other one, x is equal to 0 and x is equal to 1. And these two match what you have here on the picture, right? 0 and 1, the x components of those 2 points, right? So then this is how you would have done it if you were not able to see the image. Okay, so I think this is it pretty much, because as I said, the area is given by these two, the sum of these two integrals, right? Now, over here, you want to see this as x raised to 1/3, because then you apply power rule, you integrate. And similarly over here, you want to do that, right? This term x squared, they just you just apply power rule on them, and then you just plug in your bounds of integration, right? I don't think you are learning much from me by seeing me do that, but yeah, I think that's it. So let me know if you guys have any questions on these problems that I have gone over. And I don't plan to upload any more videos. Okay, this should be good enough. Just make sure to practice. Okay, practice integrals with U substitution and change of bounds, and practice also derivatives. Okay, I think it's going to be pretty sad if I find people that don't remember the quotient rule, the product rule, and so on and so on. Okay, don't forget those, because the derivative problem that I plan on giving you on the exam 3, will involve remembering the power rule, not the power rule, the quotient rule, the product rule, how to take the derivative of e to the x, how to take the derivative of e raised to some function, or how to take the derivative of ln of some function. Okay, so knowing those rules of differentiation and knowing the rules of integration, all of that will be super useful for this exam. Okay, those are the basic moves to solve problems, so you should make sure that you know them very well. Okay, so I now stop this recording. I wish you guys and girls good luck on this third exam. Okay, see you guys on wait, I want to stop this, stop share. See you guys on Monday. Please, as I said before, try to show up I would say 10 minutes before the beginning of class, so that I can hand out the exam, and you guys can start maybe 5 minutes early or something like that. Okay, that's all. Yes, good luck and have a nice weekend of studying.